In our last video on enolates, we are continuing to look at conjugate addition by enolates, and this time focusing on the Robinson annulation. So this is an example very similar to something we've seen where we have a beta diketone and we are reacting it with an alpha beta unsaturated, in this case aldehyde. We treat this with hydroxide. What's going to happen? These are the most acidic hydrogens, and so the hydroxide will pull off a proton to generate the enolate. The enolate will do 1,4 addition. And so that will add here, pushing these electrons up, and then these electrons will come back down and grab a proton from the solvent, for example. And so what we will get is something that looks like this. We have our CH3, C double bond O. This was our enolate. And this is what used to be our alpha beta unsaturated aldehyde. So this was a Michael reaction. But keep in mind, we still have base present and we still have several sets of acidic hydrogens. So it's possible then that the hydroxide could grab off one of these protons, one of these protons, or one of these protons. Even though these are the most acidic, if this gets pulled off, well, nothing else productive can happen, and so it'll just equilibrate. If these get pulled off, well, still nothing else can happen, but if this gets pulled off, this is where it gets a little bit interesting. Notice this one is the same as these. So if the base pulls off one of these protons, then we get a new enolate. So we have this, which is connected here. Notice we have an aldehyde, and we know that nucleophilic addition to an aldehyde is better than nucleophilic addition to a ketone. Furthermore, our nucleophile, 1, 2, 3, 4, 5, 6 carbons away. So we can get intramolecular nucleophilic addition. So this can add here, pushing these electrons up onto the oxygen. How can we draw this in a way that makes sense? So here is our CH2, which is connected to the carbonyl, which is connected to the CH, C double bond O, CH3. This CH was already connected to the CH2, CH2, CHO minus, and this is the new bond that formed. Now from here, our O minus can grab a proton. I'm not going to do all the color coding anymore, but we can have this 6-membered ring. This is a carbonyl. Here is our OH, and here is our other ketone. In addition to this OH, keep in mind we have 2 hydrogens here, and this can lose water. We're still under basic conditions, so we're going to lose water to give us this. So notice we had a Michael reaction followed by an intramolecular aldol condensation. So the Michael addition plus the intramolecular aldol condensation, this is the Robinson annulation, where annulation means ring forming. So the Robinson annulation. So what are we looking at then? We end up with an alpha beta unsaturated ketone. We also have another beta carbonyl. So we could do reactions specifically to the alkene. We could do reactions specifically at the alpha beta unsaturated carbonyl or at the isolated carbonyl, or we could generate an enolate here and do another reaction. So it's very powerful because not only did we form several new carbon-carbon bonds, we also formed a six-membered ring, and we also have additional functional groups that we can convert to other things. Now, when you do the Michael reaction that we looked at in an earlier video, how do we know when it's going to stop at the Michael reaction and when it's going to do more? Well, some of it depends on the stoichiometry and whether it is likely to have an intramolecular or intermolecular reaction. Some of it depends on the nature of the compounds that you're working with. In our earlier video, we had a ketone rather than an aldehyde, so that our product here, this was a ketone, and so if the enolate formed and we were adding to a ketone, that's not as favored as addition to an aldehyde. So there are several different cases where it is more likely for the Robinson annulation to occur. But this is this is complicated, and so I'm not expecting you to predict when a Robinson annulation is going to happen, but instead, I would like you to think about explaining when it has happened, showing the mechanism of how it happens. So let's look at an example on the next slide. Now, I might ask you to outline a reasonable mechanism for the reaction below. So we have this beta dicarbonyl compound, and we are reacting it with an alpha beta unsaturated ketone. And in the presence of hydroxide and heat, we get this bicyclic product. How does this work? So in this case, I'm telling you what the product is. I need you to show me how we got there. Well, first of all, if we have both of these species present and we treat it with hydroxide, this is the most acidic hydrogen, so this is the one that will get deprotonated. So hydroxide will grab off this proton, and we are going to get this enolate, and then this enolate can carry out conjugate addition to the alpha beta unsaturated ketone, and that is going to lead to this intermediate. Now, obviously, more happens, so what can happen next? There are no more hydrogens here, so we have these positions that are alpha to a carbonyl, this position, and this position that are alpha to a carbonyl. And any of those will get deprotonated, but they can equilibrate. The only way something interesting happens is, and the only way that would lead to the formation of this product would be if one of these hydrogens was deprotonated. So the hydroxide can pull off one of these protons, which is going to give us, here's our CH3 and our other carbonyl. And now we have our CH2, CH2, C double bond O, CH2 with a lone pair and a negative. Notice in our final product, we have the six-membered ring, we have the carbonyl up here, we don't have the carbonyl here. So let's make it easy for ourselves and show this enolate adding to this one, even though it is equivalent to this one. Let's just add it to this one. So if these electrons come over here, add to the carbonyl carbon, push these electrons up onto the oxygen, that is going to give us, we have this is an O minus. Here we have a CH2 connected to a CH2, connected to a C double bond O, connected to a CH2, which is connected to what used to be the carbonyl carbon. Now the O- can grab a proton, and then hopefully I can draw this a little bit neater. So we have this, and that is connected to, here is our CH2, here is our carbonyl, here is our other CH2 that's now connected to that carbon. So we have our original six-membered ring and a new six-membered ring. This is still under basic conditions. We have heat. So from here, this can lose water. So we're going to lose the OH from here, and if we lose one of these H's, that will give us an alpha beta unsaturated ketone, right? It gives us a conjugated ketone. So we get this as our final product, and this matches what was observed. So that means what we're looking at is formation of the enolate, and then Michael reaction, so conjugate addition leading to this, but then this can react further to generate this enolate, which can add here or here. It'll lead to the same thing. This is the aldol addition, and then because we lose water, it is overall the aldol condensation. So Michael reaction followed by intramolecular aldol condensation, or the Robinson annulation. So again, I'm not expecting you to predict when it is going to happen, but I do want you to recognize it. I want you to be able to explain it. And overall, I want you to recognize the power and the flexibility that we have in the many types of reactions that we can carry out. So we're looking at reactions that it's not just a one and done, but it's a reaction that gives us a product that can also undergo additional reactions and additional reactions and additional reactions so that we can carry out multi-step synthesis, leading to compounds that are much more complex than our starting materials. So this wraps up our chapter on enolates. So we've seen enolates carry out nucleophilic substitution, nucleophilic addition, nucleophilic acyl substitution, and now conjugate addition.